No.
Good morning, everybody. I'm glad that you're able to join us today. I'm Paul Michael from Milwaukee School of Engineering Fluid Power Institute. Milwaukee School of Engineering is a private university in downtown Milwaukee, 6 blocks from Frigid Lake, Michigan. We're known for our ambitious students and our long-running partnership with industry, and especially the National Fluid Power Association. The consortium at MSOE is a partnership with them, and together we develop quarterly webinars that highlight market-ready technologies and provide actionable solutions to help the fluid power industry and its partners. Today's topic is right out of the NFPA roadmap, leak prevention. I have to tell you, I love big machines, but I hate leaks. So I'm very excited about what we're going to be talking about today. We've got Andy Frayling from Advanced Hydraulics, Chad Chapman from Gates, and Trevor Combs from Trelleborg here to share their expertise in fluid power and leak prevention. Before I introduce Andy, I want to mention that MSOE will award you with continuing education units or professional development hours for your participation today. Just send me an email and we'll have a certificate prepared and sent to you. Here with me is Andy Frayling. He's president and owner of Advanced Hydraulics. There's only one D in Advanced Hydraulics. His experience in hydraulics began when he was 9 years old working on a neighboring 25-acre farm. His first invention came 9 years later, where he modified a rotary hoe with hydraulic wings. So he's been working with hydraulics since he was a young pup, and he's got lots and lots and lots of experiences. Decades of experience in designing, troubleshooting, repairing hydraulic systems across all sorts of industries. He's collaborated in projects ranging from the stadium roof lifts to mining equipment, and also for projects at the Fluid Power Institute. He's a great machinist, a great designer, and a great guy to work with. Why we love to work with him at the Fluid Power Institute is that when we come to him with a design or an idea, he always adds his special sauce, a little something to make it better. And so I've asked him to join us today because I want him to add a little bit to a special sauce to our presentation. He is a certified fluid power specialist and serves as an expert witness in hydraulic related cases. He brings a proven record of innovation, including a U.S. patent for rail car braking technology. And he's going to add practical insights to our leak prevention webinar today. So with that, I'd like to get started here. First, let me thank the people that have participated in the leak prevention task force. We had quite a number of contributors. Special thanks to people that gave a close reading to the document and provided editorial suggestions. John Frey, Tom Skinner, Dave Tetzlaff, Catherine Quigley, Mike Maxim, and Trevor Combs. You all had some great suggestions to make the document better and improve it, so we appreciate your contributions. The first thing we did in the leak prevention task force, and you know NFPA loves to get the pressure, the pulse of the fluid power community, as we did a survey. And the first question we asked is external leakage a problem for your organization? And 3 out of 4 companies reported that, yep, we've got external leakage is a problem that we'd like to see addressed. Why do they want it addressed? Why is this an important problem to be addressed? So we said, which has the greatest financial impact on your organization? Number 1, customer satisfaction. You know, in the fluid power industry, we want them to come back happy and love our products, and we want those satisfied customers. Downtime, we know that that's a priority for our industry. That's the number 2 problem that they see. And then finally, warranty costs. So the bottom line is this leak prevention is crucial for the sustainability and continued success of the fluid power industry. And so we're focusing some effort on that today. So we're getting into the document, the white paper, and this will be posted on the website in a couple of days, along with the recording of our presentation. And so it starts off by talking with application factors. We have factors such as component accessibility, temperatures, compatibility, things like that. And I've enjoyed going over these considerations with Andy, and he had something really interesting to say about how fluid contamination causes leakage. And I'd like you to talk about that a little bit, please.
Fluid contamination causes a circle in the system because when you have contamination, you have wear components, seal components, leakage, increased temperatures, and then the circle begins bigger and bigger and bigger. So you have more and more leaks. So by correcting contamination, you stop causing the component wear, which then stops causing the heat, which stops causing other issues.
Right, hardening of the seals could be one of the issues.
Or hoses, or expanding and contraction of fittings over and above what they're normally operated to run at.
Okay, cool. Good insight. The next section goes into some design considerations and talks about all the different kinds of connectors in the fluid power system. I mean, it really is the number of ways to make our highly modular systems come together is just incredible. And so Andy's going to take a little bit of time talking about 3 of these types of ports and their different properties. So he's going to start off with the O-ring face seal and show us a little bit of that.
Camera on so they can see
Is
it.
Camera on? Escape.
We can see it.
You can see Andy's hand?
Okay.
Yeah, we can see his hand.
Okay.
All right. So the O-ring face seal actually has a positive seal in the face of the fitting. Therefore, when the face hits, it has a positive seal when you tighten it correctly. Most of the other fitting types, like the JIC, here is a compression metal to metal seal. Also with the bite tight, which this has to seal on the ID and the OD. And all these fittings take a certain amount of skill to put together, which the O-ring seems to be the best for most applications just because it does have a positive sealing surface, which does not have to require a metal-to-metal fit. Because when you deal with a metal-to-metal fit, we did this in our shop and purposely over-tightened this fitting to cause damage to the seat. So even if you replace the hose on this fitting, you're still going to have a damaged seat, which then will cause leakage. So there's various types of other things with the SAE adjustable fittings. This is the O-ring groove where it sits. Numerous times these are installed improperly. And what happens when you install them improperly is you drive that O-ring down into the thread and then you get seepage over time. The correct way to do it is to back up the nut, let the washer come up to there, hand tighten it till you seat the O-ring, and then you have a 360-degree turn before you tighten your jam nut. That way that O-ring does not jam into that first thread. So a lot of this takes some skill. The O-ring face seal takes the least amount of skill. The others all require some skill set. So, and it's a positive seal. So therefore, it's the superior fitting as of right now. The problem with it is you do have a little bulkier of a connection, right? The nuts are bigger. The physical size is bigger than this is a 12 JIC, this is a 12 ORS. So you physically have size difference. There is a little bit of extra cost to that fitting also across the board, depending on how you look at it, but it does prevent more leaks. The downfall, again, is O-ring material and compatibility, making sure that that fits for your application.
Very good. Thank you. We'll look for questions in the chat. So that covers the 37 degree and 24 degree. Tell me about the 24 degree one.
The compression fitting is made up of obviously the body and the sleeve, which the tube has to be inserted all the way down to the bottom. They do make a tool to preset this to the tube, but most people, if they're doing a field repair, they'll push the tube all the way down. You have to hold the tube all the way down and then tighten this to get this to crimp to the ID and to the OD into the seat. The issue with that is you can over tighten that fitting and cause an internal crack on the tube because this is biting into the tube and deforming it. So and manufacturers vary on their design of that fitting. So it's more so that you can't interchange. JIC is JIC. Pretty much across the board, they're going to work. Where a bite tight, manufacturers make them differently, so they're a little unique to themselves. If you go with one, doesn't mean you can directly take that off and put another one's on.
What do you mean by JIC?
37 degree is JIC.
Okay. All right. Just to make sure that you know that there's
Yep.
some that we have in our industry.
Yes, there's different O-ring face seal, ORS. There is some different terminology across the manufacturers that is not unified for identifying all the fittings. So there is some variance in the language,
Okay.
you know.
All right.
So like this particular fitting, you know, takes a Boss O-ring, which I forgot to bring up.
We can bring that up.
Okay, so there's some variance, yes, in the industry.
Okay. Very good. All right. Let's see. So that covers
We have a question.
Sure.
What are your opinions on securing style O-ring? Assembly issues with normal O-ring falling out, pinched, etc. So the securing style O-ring.
There is various types of the O-rings that have come out. There's particular manufacturers, OEM manufacturers, equipment manufacturers that make their own O-rings for some of the particular fittings. I've used quite a bit of them. Some of them do work very well. There is a downside to some of the cost, you know, so there's pros and cons. It does work on most cases. It has to be applied correctly, and cost, if it's an issue, that's probably not the way the most average OEM would build.
So this is for people that are worried if they use the O-ring face seal, that during the assembly process, the O-ring's going to fall out.
Right.
Is that it?
Right. And there's a lot of different seals you can put on that face. And it would take me a long time to go through all of them.
We'll talk about that in a little bit, though.
There's a lot.
So
Here's another question.
Okay, great.
What are your thoughts on the O-ring in the JIC male fitting? And also it's noted that JIC stands for Joint Industry Council.
Are they talking about the O-ring directly on the face?
It doesn't say it. Your thoughts on the O-ring in the JIC male fitting?
Male. The O-ring, it's been my experience that they work well. The issue is they're more susceptible to collapsing the ID of the actual fitting. So there's some manufacturers that take and put an O-ring right here on the seating surface, and they work well. The issue is a lot of mechanics over tighten that, and then they start collapsing this ID, which if you do maintain the proper torque specifications, they do work and they do work well. But again, that mechanical aptitude versus functionality sometimes is a hard blend to get right.
Okay, great comment here as well in the chat, suggesting you join the ISO TC 131 SC7 Work Group 3, working on technical report on usage, design, storage, assembly material, etc. So yes, joint standards. You can contact Ben Brown at NFPA to get involved in the standards development committees.
Awesome. In the document, we have quite a bit dealing on hose fittings with the selection and so on, the routing, clamping. And we're really excited because Chad Chapman from Gates is going to be presenting on hoses next. So we're looking forward to his presentation on the topic of hoses. But there's a lot of that in the white paper as well. Next, we get into, in the white paper, the assembly practices. And one of them is the split flange port. And Andy and I, we were talking about how do you do this 4-bolt tightening pattern when you've got a heavy hose with a flange on the end and you're trying to get it bent into position and stay there at the same time you're going from one half to the other half like that.
Yeah, there's a couple tricks to the trade. The one thing is taking a split flange half like this and making sure that you have plenty of room between the face. So when the fitting comes in, it goes to connect upward into the seat and not coming across the face. So you don't roll the O-ring out of the face and damaging this or pinching that, and then bringing it uniformly in to secure it, or pushing it in or holding it in as you snug the bolts and then do your bolt pattern. Because a lot of mechanics struggle with that O-ring extruding during assembly. I've done it myself. So, I mean, it happens.
So when you're sliding that thing in the place, if you slide it in, you might wipe the seal out.
Yeah.
Oh.
And that's one thing that, by leaving the bolts loose and far enough away that you don't make contact to the O-ring till you can get it straight push onto the face and then snug your
And then
bolts.
you do the pattern of attaching it that way. Cool. All right, the next one is, you mentioned that the O-ring boss elbow connector adjustable stud ends is a source of leaks, and you made a lot of money from fixing these things, I guess.
Yeah.
So can you kind of explain?
Well, I'll go through it again. I mean, this is the example. We purposely damaged this one where we drove that O-ring into there, which we see so many times, where this one's done, it's sitting in the groove proper. Again, hand tighten this down, and then 360 degrees, you have, once that O-ring seated, that you can adjust to turn, and then tighten your jam nut, holding your fitting. So you're not grinding that O-ring, because a lot of people don't use lubrication on their O-rings, which they should put a little bit on when they assemble, but they don't, they should. So it goes together without leakage.
Mm-hmm.
And that O-ring itself is a Boss O-ring. This O-ring is a different cross section than an 1/8 or a 32nd or a standard O-ring. So many people have an O-ring kit that they think they can just grab that O-ring out of there, and it's not the appropriate O-ring for that application.
So if the diameter fits, that may not be the right size if
Right.
the cross section isn't right.
Correct.
And they have a different cross section.
Yes.
Is it on the face as well as on the Boss, or
the O-rings are made, the cross section of the O-ring is here and here. It's because it's round, and the ID and OD are different. It's not a standard 1/8 inch 32nd cross.
Okay.
So, and typically they're a 90 durometer. They have a little bit, they're better for a static sealing application. The durometer is a little different, but
So they're a little bit harder and
yes,
better for static.
yeah, static loading.
Mm-hmm. Cool. Good insight. Next, we want to talk a little bit about conductor cleaning. We talked earlier about contamination being a concern, and Andy, why don't you talk about, if you would, cleaning with compressed air? What do you think about that idea?
Generally, you don't get enough CFM to get the hoses blown out properly. Most shop airs are not clean enough, including probably my own, even though we do a lot of filtration and everything else on there. If I'd actually tested, it's probably not clean enough. I mean, if you have to do something, do that. It's not really adequate for cleaning properly.
Mhm. All right. Next thing is we want to talk about leak detection. And the white paper has ways to troubleshoot leakage in all of the items listed on the table of contents here. We were talking about the 37-degree flare connection, Andy, and how hard it is and tricky it is to detect that leaking. Can you explain that, please?
Well, the starts with your fitting, right? Like we over tightened this fitting and damaged this seat, started to collapse the ID a little bit. Okay, most people will put on a new hose. Well, that's not going to solve the problem.
Okay.
Okay, so then we actually made some samples of tubing, right? Where this one's made correctly. This one is been over tightened to the point where you cannot spin the nut anymore. So they start twisting the tube and then they cause more damage to the tube. Most of your tubes, when they get damaged, will crack right here. And it's very, very, very difficult. Can they see that well enough on there? It cracks right there, right at the bottom of the seat.
Mhm.
So it's very difficult to see that little tiny crack.
So the cracked flare is where you're talking about a significant problem, and you just got to replace the whole tube.
Or you cut it back if you, depending on how the tube run is done. Sometimes you
Mhm.
can cut it back and reflare it.
Okay.
Okay. But again, that crack, it starts out usually as a drip, and then somebody goes to tighten it and they make the drip a little worse. And then they crank on it even harder. Now they damaged the fitting, and now they damaged even further trying to repair, because even if you do reflare, you're still going to have a damaged fitting. So now you got to replace your fitting and your tube because you didn't identify the leak correctly.
Do you think it's true that if you see a leak or a little drip, that you better take action right away because ultimately it's going to create a huge mess?
The leak in itself, yes. What that's telling you is something's not happy, right? Something's not right. So that little leak, oh, we'll leave that go. And then all of a sudden, oh, it blows out like a hose or whatever. Hoses are more prominent to blowouts when you see a slight bit of leakage and you just get that drip. And then all of a sudden, an hour later, the whole hose blows because, they're more susceptible.
The braids are.
Yeah, it's already compromised.
Mhm.
The fitting or the crimp is already compromised, which we'll get into later. So with a tube and all the other ones, a drip doesn't get better. It's not going to fix itself.
Mhm.
And usually I like to see people investigate, why is it? If it didn't leak before and it's leaking now, why? There's something wrong. There's something wrong with the tube. Your clamp broke. Now you're putting more stress on your tube. Now you cause the end of the flare. Clamping is one of the biggest issues that causes leaks
Why is that?
because it creates vibration and it creates pressure on these compression joints. With that vibration and twisting and moving on that, the compression joint just keeps digging in tighter. And that causes a crack.
Oh, okay. It gets a lot of torque on it and digs
Yep.
in and causes
And
that crack.
And I've seen people repair leaks and then it comes back 2 weeks later because they didn't repair the clamp. You
Mhm.
have to repair your clamping and do better clamping, period. People don't clamp good enough.
Stop that vibration and things will be much happier and a lot less leaks.
Very much happier.
There's a section on the sealing of major components. We've got static sealing and dynamic seals. We've already talked about the special O-rings for the face seals. I was wondering if you've had experience with the non-traditional geometries of O-rings, the X rings, the square rings, the dual seals and stuff like that.
We've used all of them.
Mm-hmm.
That goes more to some of the specialty fittings and O-rings that you can use on these connectors to make them a better one. The dual seal and stuff like that is more dynamic for heads in glands and so on and so forth. Well, they'll take more impulse cycles and seal better because of the pulsation. You're going from 0 to 5,000 psi in 20 milliseconds.
Mm-hmm.
That kind of impulse, an O-ring in itself usually doesn't hold up very well to that cycle duty. It'll start rolling, it'll start doing other things.
Extruding.
Yes.
Mm-hmm.
Well, if you run your backups correctly and your clearances are tight enough, I don't worry about extrusion as much because when I do stuff like that, I run tight clearances. So, but the dual seal and everything else, yes, they add to a more heavy duty cycle, more impulse from going from 0 to a higher pressure in a rapid rate. And then the decompression of that actually causes a lot more stress on the components.
Interesting. Thanks for your insights. From Trelleborg is going to be presenting on linear sealing systems, and we're looking forward to. He's got a great presentation, and we're looking forward to hearing that. But are there any other troubleshooting tips you want to give to our people in the audience that say, if you want to make sure that you don't have leaks, this is one trick that you ought to consider?
Yes, this is a connector, and these are silver soldered joints. So this is actually a 3-piece connector. Works in most applications. Static loads, not very high impulse and everything else. You start getting into high impulse areas and everything. This is a forged fitting. This is literally one piece of metal and bent after. Much, much, much stronger.
Oh.
And can handle that kind of cycle duty numerous times. These type of ends can break off, or again, clamping, impulse, hose whip on this end will cause a lot of stress and cause it to fail. So make sure you use better quality product, forged fittings in higher dynamic areas.
Fantastic. So, are there any questions for Andy?
No questions in the chat or in the Q&A right now.
Great. All right. Well, Andy's contact information is there, and we'll be sending out a recording of this presentation so you can learn more. Let me stop sharing here. And I want to take this moment to introduce Chad Chapman. Chad is a mechanical engineer with 20 years experience in the fluid power industry. He currently serves as a product application engineering manager at Gates, where he leads a team that delivers guidance, recommendations, and solutions to customers across diverse applications. He's passionate about problem solving and collaborating with industry and collaborating with others. He likes to work closely with customers and try to get optimal performance. What does that mean? Prevent leaks, stopping leaks. He's got a lot of industry experience and a lot of hands-on experience was going to shine through with his presentation. Also want to say, Chad's an MSOE alumnus, and let's hear from him now. You're muted, Chad.
All right. Can you hear me?
Yes, sir.
All right, let me try this over. Switch screens. Thought I had this all figured out earlier, so apologies for that. Paul, thanks for the great introduction. Again, I work for Gates. I'm an application engineering manager. So part of my job is recommending products, which I'll get into here. But thank you for inviting me to talk about leak prevention. So what I like to do is talk about it from best practices as a hose and fitting manufacturer looking on the hose side. We had a lot of discussion on the coupling and connection. Now we can get into a little bit more on what it means with the actual hose assembly piece when it gets put on equipment. So when I thought about leak prevention, I came up with 3 categories that I wanted to bring up and discuss as part of some best practices. First is the component selection. We have an acronym called STAMP that we use to make sure that we're selecting the right components to meet those application requirements or customer needs. All right. The next piece is putting that coupling onto the hose. That's a very critical process, which can lead to issues down the road. It could cause leaks or blow-offs, etc. So I'll talk a little bit about that stuff. And then installation, putting the hose in service, right? There's some routing, there's some best practices, torque specs. We touched on that a little bit already. And then try to just reduce the overall unnecessary threaded connections maybe in the system. So I have an example on that. All right, component selection. So we have a term called STAMP. It's a 7-letter acronym. This by far has been the greatest tool that I've used at Gates on the fluid power side. And this really helps define what those application requirements are to make sure that we can select the right components to make sure we meet those application needs or customer needs. So the first letter S, that's size. That's pretty straightforward. That's the ID of the hose or the threaded end size, the termination size. What size threaded end do you have on the fitting? And then temperature, T for temperature. So it's not only what the internal fluid temp is that's going through the hose, but you also got to be aware of maybe any external heat sources that you may get where it impacts the outside of the hose, which could also cause to some premature failures. And then A is for application. What type of application is this hose or hose assembly being put into? Is it a static application? Is it a high impulse? Is there a lot of vibration? Application. What is the hose supposed to do? Right. So that's an important ask when we're trying to find the right hose or fitting components. M is material or media being conveyed through the hose or material compatibility, however you want to look at it. Basically, is that hose compatible with the fluid that's running through it? Okay. That's what the M stands for. And that's one of the most critical pieces. Hydraulic systems tends to be pretty straightforward with the type of materials, but you also got to worry about the cover. So if there's the cover of the hose is being exposed to a chemical or other fluids, again, you don't want that chemical or that cover to be degraded over time, and it could be a material compatibility issue on the cover if there's some sort of external excess fluid there on the outside. P, well, that's pretty straightforward. Pressure, okay. Well, maybe not always straightforward. Andy told me to talk a little bit about vacuum, but pressure, right? What's the max pressure that hose assembly is going to see? There's an operating pressure, but are there surges? Are there spikes in the system that you need to account for? Is it a high impulse application? And then if you have a need for a vacuum or suction, use a hose that's designed for suction. We have a lot of low pressure options with the helical wire, and so the hose doesn't collapse if it needs to be used in a suction application. Not all hydraulic braided products have a full suction braiding on, so you got to be careful of that. E is for ends, the type of ends. We just got done talking about JIC and O-ring boss. So what threaded end do I need, and what type of coupling style works with that hose? That's what we talk about when we say ends. And then D for delivery, that's the fluid going through the hose, how that fluid is being delivered through the hose. Okay, so you look at flow rate, fluid velocities, pressure drop. Do you have the right sizing of your hose so you don't have a significant pressure drop across the system? Fittings also impact that as well. So that is when we talk about design considerations, this acronym is one that we go to a lot for making sure we pick the right components. So I'm going to cover some examples of what it looks like when you don't pick the right components. Okay, here's a picture of a hydraulic hose. You have bubbling on the cover. So one possible cause is that hose had that fluid going through the hose is not compatible. So the fluid's permeating through to the cover and getting trapped underneath the cover layer. So incompatible fluid. Rubber is also porous. So gas will permeate eventually through the hose. So if, in a worst case, if you have a lot of excessive air trapped in a hydraulic system, maybe there's a potential that air permeates through the hose and causes some bubbling like that. So obviously solutions for that would be choosing a hose that is compatible with the fluid being used. There's chemical resistance tables out there that we refer to all the time. Typically each hose manufacturer will have a compatibility chart that you can reference. And then for the trapped air, pin pricking the cover is also an option to allow that air gas to escape out of the cover so it doesn't bubble up. Here's a picture of two hose examples where the cover is hardening and cracking on the outside. So possible cause, excessive heat, right? So internally, maybe it's too hot, or externally, it's next to an extreme heat source like an exhaust. Also ozone or weathering too. That can impact if the hose is outside, being subject to the elements, you could see that. And so solutions to that would be using a higher rated temp product, using heat guard or heat sleeving, or rerouting away from a heat source if there is an external heat source to that cover, causing the cracks. Lastly, it is a recommended practice not to intermix coupling and hose manufacturers. Okay, so here's an example where you have a Gates fitting on a competitive hose. Every manufacturer designs the hose and fitting to work with each other. And we have things called crimp specs that we make sure we test. We test the SAE, and we make sure that specific fitting and hose that we recommend will meet those performance requirements of SAE. We can't guarantee, using a competitive product that you'll get the same performance. And sometimes that could lead to, if it is mixed or matched like that, you have a really high chance of blow-offs where the coupling blows off the hose or leaking as well. But typically, you don't see this much, definitely not on the OE side, but you'll see this on occasion in the aftermarket replacement market. So, just possible causes, just improper training, people not knowing what they're looking for, what goes with what. I'll talk a little bit about that here when it comes to the assembly fabrication. And just follow, I guess the solution here is follow the manufacturer's recommendations when it comes to, I have a hose, I need to use these fittings and these crimp specs. Okay. All right, now I'm going to jump into the component assembly, or the assembly fabrication. So this is where I have a coupling and a hose, and I need to put them together. So there's a couple of different attachment methods. I know the white paper talks about there's crimping, there's swedging, there's field attachable. I'm going to focus on the crimping, since that's the majority of what's out there in the industry today, or the preference as well. So the picture on the bottom right here, you can see you have the stem that goes all the way into the hose, and the ferrule on the outside, which gets crimped down and bites into the hose. Okay. So that process, that crimping piece, and what to crimp that ferrule down to is typically spelled out by the hose manufacturer on what they publish, what we call crimp specs. There's a bunch of, each manufacturer will have different tools. We have online tools, crimp charts, etc. But it tells you for this size, this hose, this fitting, and this machine, I need to use, these dies to crimp it down and hit this crimp outside diameter. So when it comes to actual crimping, there are three critical pieces to having a good crimp. One is the insertion. You want to make sure that that fitting is fully inserted into the hose, that there's no gap there. Because if there's a gap, again, that's a high likelihood it could lead to a coupling blow off. Okay. So there's things you could do like marking the depth, like the picture shows here. And then when you put it on, making sure that that mark kisses up or is hidden by the ferrule. Crimp length is another one. So a lot of times, most of the hydraulic assemblies that we have an offer that it's going to have a full crimp length, but there are some manufacturers and styles out there or coupling hose combinations that require maybe a bubble at the top or a tail on the back end. And that's what we call like the crimp length. So that is, again, is specified by the manufacturer for that exact fitting and hose combination. And then lastly, crimp diameter. Crimp diameter is probably one of the most crucial pieces. That's when you crimp that ferrule down and bite into that hose, that's that final diameter. So when a hose and fitting manufacturer comes out with crimp specs, we do all our performance testing to hit SAE based kind of on our nominal crimp OD. We do it over a range of the tolerance is generally plus or minus 10 thousandths, but we do it over range to ensure that we can get good performance and try to hit that nominal crimp OD. Okay. Always, I guess, too, it's always important after you crimp to make sure you measure it and check it, right? That's the most critical thing. And if you notice you're not hitting the right crimp OD, the machine might need to be calibrated. And I would not recommend using that assembly if you're not hitting, if the crimp OD is outside of tolerance. Here's some examples of what over crimped and under crimped looks like. So the image on the left here is over crimped, so that ferrule is completely squished down on the hose. It's crimped too tight. And then, so what happens there is you're just cutting into the braid reinforcement, and you're causing, you can cause potential leak paths to leak out behind the ferrule there on the backside of the fitting. And you can also have, if you cut through a good portion of the wire, maybe a potential blow off or premature failure or rupture at the backside of that fitting. Something that's over.
Oh,
yeah.
Chad, we've got a question and maybe this fits right here can you describe how to measure the crimp diameter?
Yep. So you see here, it's always best practice to use a caliper, right? And when you measure the crimp diameter, you want to measure, see, when you have dies like that machine there on the right corner, there's die fingers. And there's, like for us, we have 8 die fingers. I think that's pretty common. So you'll have 8 ridges that get formed on the outside of that crimp. And you can kind of see it in that picture where he's measuring. And you want to make sure you measure on the flat, so in between the ridges, and generally like middle of the ferrule area. Okay. And you want to turn the hose around and take multiple measurements. So you get a good average. Hopefully that explains it. There's so much to get into with all this. We have 2-day classes where we cover a lot of this stuff. So I left out the image of where to measure and how to measure. But hopefully that is a good description of how to measure. All right, the image on the right is under crimp. So I didn't crimp it down all the way. It's loose. So again, if it's loose, it's not biting in enough, and it is likely susceptible to a coupling blow off or a blow completely off at a higher pressure. or leaks too, right? You'll get, it's not sealed down, crimped down tight enough, you'll get some leaks. And here's an image of a correct full crimp, what that looks like. So the other piece, we talked about crimping, but when you're building an assembly, you've got to cut the hose, and you've got to, apologies here. You've got to cut the hose, so that generates some debris from the rubber and the steel that's in the hose. Okay, so we talk about hose cleanliness. So we don't want to introduce any foreign contamination to the hydraulic system, right? We don't want to add any debris into there. We want to make sure that that hose gets cleaned out. So if you don't clean it out, we talked a little bit about cleanliness, Andy hit on that, but that can lead to component wear in the system. You have, debris or chunks of rubber or metal being run through the hydraulic system that can reduce your efficiency, create blockage, or even early system failure. Okay. So cleaning, you want to make sure that that's another step in the assembly fabrication process. And there's a couple of different methods. Some folks out there use shop air. We'll use foam projectiles or fluid flushing. Okay, so you can see here's the picture of using a foam projectile. You got a foam pellet that you put at the end of a nozzle. There's a hand tool, and there's also a workbench station that you can use. But you're basically blowing that pellet through the hose to clean out that debris. And you'll blow it through one way, and then do another pellet through the opposite direction. Then a lot of times too, you can crimp it and then do that same process again after it's crimped. Just kind of depends on what that OE cleanliness requirement is. So there's different ways to achieve the different cleanliness levels out there.
Hey, Chad, we've got a question here. Yeah, maybe it's a good time for it. The question is, aren't hose and fittings following certain standards in terms of dimensions for interchange between different manufacturers?
Yeah, I mean, yes, typically SAE is the predominant one, SAE, ISO. There are ID tolerances. Just because of that, though, that doesn't mean they're interchangeable, right? That's not the point of, doesn't mean they don't fit together. It just means that as a hose manufacturer, when we release a hose to the public, we design that hose and fitting that we make to work together, and we run it through vigorous tests. Impulse, burst, you name it. We run the gamut of tests on that specific coupling and fitting. Okay, so if now you go and you take a competitor, yeah, that competitive coupling may fit on our hose, right? But what's the crimp spec? What's the crimp diameter? What if they change the coupling design? We don't control any of that. So that's generally why you don't want to intermix between fitting and hose manufacturing. All right, we're going to look at some problems that originate with the improper assembly fabrication. So here is a picture. You can see where the ferrule is extremely crimped down. It's over crimped. It's crimped too tight, and you'll have some leaking behind the ferrule. So obvious cause of this, it's crimped too tight. They didn't follow the crimp recommendations, so they'd have to replace the assembly, start over, make sure that they're following the right crimp recommendations, and if necessary, seek the proper fabrication training from the manufacturer. Here's another one where you have coupling blow off. So here's two pictures that show a fitting blown off the hose end. And so again, this could be for over or under crimping, or the bottom right picture, because of how much cover material or how little cover material is removed there, it looks to me like this did not get, the fitting did not get fully inserted into the hose. So there wasn't enough bite, so it blew off. Again, solution to this, you'd obviously have to replace this and follow the right crimp specs. Again, possibly recalibrate your machine if you're not hitting those crimp diameters like I mentioned earlier. All right, now we'll get into the last section, which is the installation best practices. So got our finished assembly. Now we're putting it into the application, and we're going to look at hose routings and eliminating unnecessary connections and torque specs. You can see the picture here. Some mobile equipment applications or machines have a lot of hose in it, right? Because sometimes we used to like to joke that hose is usually an afterthought. It's the last thing that gets thought about. So obviously there's different techniques and routing guides that you can utilize, and a lot of the manufacturers publish information on best practices. We do. There's also some best practice info in J1273. Okay. And typically too, when you start introducing a lot of threaded connections or stacking adapters, that's just adding more leak points to the system. So you want to try to keep that to a minimum. And then torque specs. Andy talked about cracking the seat on that flared tube for that JIC. Again, you want to make sure that you're following the right torque specs, which again is called out in J2593. So we refer to following the SAE torque recommendations when it comes to the different SAE thread configurations. Just covering some routing tips. Minimum bend radius, or MBR, that's probably one of the most critical features that you'll see hose OEMs spec out, and that's how much the hose can bend. And when we publish a minimum bend radius, so this example says it's a 2-inch minimum bend radius, you don't want to go past that. That hose is designed not to go past that, because once you do, you can reduce the service life of the hose, and that could lead to premature failures, leaks, etc. So the picture on the right shows that minimum bend radius being exceeded, right? You're going beyond that MBR. All right, tight bends. So cover some really generic pictures here that show some tight bends where you have the picture on the left, you have the fitting going horizontal, and then a tight bend right past the coupling there, and it comes down, and you can kind of see it's exceeding the minimum bend radius. So you can clean that up with using a 90-degree adapter or a 90-degree fitting. Same thing here, you got another tight bend. You want to try to get that, you want to try to extend and use a large bend radius where you can without using too much excessive hose. Same thing, another picture showing a tight bend right off the bottom left fitting on the wrong side, where it comes off that a little bit of straight length, but then has a sharp bend there. Again, you're putting a lot of stress in one area, which can lead to eventual potential leak point or weak point in that assembly. And just, again, you can clean things up with using elbow adapters or fittings. This is a picture just showing strain being put on a hose assembly. Especially the grade images are probably more a better depicting image to show that there's a lot of strain. You typically want to leave some straight length behind that ferrule before you start bending. You don't want an immediate bend right past that ferrule, because that can cause a weak point there and eventually fatigue out and stress that area where you could have potential rupture or leak. So here's an example of one that had some strain or a lot of flexing behind the fitting. And again, the bottom diagram there, you want to try to have some minimum straight length before you start your bend if possible, because that just leaves it as a potential weak point in the system. All right, and here we'll just look at some examples again of some failures right behind that fitting. Again, these pictures, all potential causes could be you had that excessive bending, not enough straight length behind the fitting, so you get a hose rupture right at the backside here, which is bad. Or two, I guess if it's improperly crimped too, right? We talked about over crimping crimping too tight, maybe like that bottom right picture got crimped down too much. So you want to make sure that you have enough straight length. You can reroute things, again, using elbows if you need to try to eliminate that strain off the assembly. And again, make sure you're using the right crimp specs in case something was maybe overcrimped or undercrimped. All right, Andy talked a little bit about this, and I wanted to just share this picture. Here you can see the code, I believe it's a code 61 flange, probably for a lower pressure application. I'm not sure here, but this one, it has that brazed flange end on it, and you can see it came off. So the brazing isn't always necessarily a bad thing, right? But there's a place for it. So if you have something like Andy pointed out, higher pressures, a lot of impulses, high vibration, you typically would want to use a forged fitting. So again, this is an example of one that either had a lot of strain. So sometimes if you have a lot of weight, like you're talking, some of these flange assemblies are large, 6,000 PSI spiral wire, 2-inch, very heavy, right? And the flange ends are heavy. So you're putting a lot of you want to make sure you don't have a lot of side load or load on that fitting too, because that could lead to issues. Abrasion's another one that comes up with hose routing. So you want to try to avoid rubbing up against things on the equipment where possible, especially if you have a lot of vibration or movement. So clamping can be an option to help alleviate that, just like the picture shows here, utilizing the right clamp size and allowing to keep things maybe tight against a section where you can avoid sharp corners or things rubbing.
Hey, Chad, I think
Yeah.
actually, I think you kind of hit on something that answers a question that's in the chat. The question in the chat, there's two of them actually. Are there hose clamping guidelines to prevent fatigue failure and hose crimping? And then are there special hose clamp guidelines or suggestions depending on the type of hose and use case?
We do have, I know as Gates, there's some clamping options, and we have some crimp specs that for a certain hose and clamp style that you're using to use. The clamps, like the P clamps that go around and are used typically a lot of times the OE is really driving that from what they have hardware when they're doing the install of the equipment. We do have some, and some manufacturers have it. It's probably an area that could be improved on more, just in general, as far as maybe best practices. But there are some guidelines that are out there for clamping, but can be hard to find.
There's another question here, and I think what the person is asking is whether there should be certain qualifications for companies to manufacture hydraulic hoses.
Yeah, I mean, really, I guess with hydraulic hoses, SAE is by far probably the biggest industry driver, and ISO. So they have, it's self-certifying, so it's not like they go out and verify that you're manufacturing and meeting all this stuff, but it's each manufacturer's responsibility to make sure that they do the testing, they have that documentation, and can verify that, because SAE and ISO, they'll have performance requirements that you need to meet. And then when OEs, come to us, they'll say, okay, we need a, J517, whatever, 100R, 16 hose, or, whatever the spec is, we have to meet that performance requirement from that governing agency, governing body. So there are requirements out there, but it's kind of self-certifying. So, I mean, you could get somebody that claims to meet it and might not. But eventually you'll see that from quality issues, right? Performance issues. All right, some pictures of cover abrasion. Here you got the picture on the right is an extreme case. It looks like it's rubbing up against something, maybe even possible hardening as well. And then the picture on the left just shows hose on hose rubbing. So you obviously want to try to avoid this. So what happens if the cover gets abraded off or cover gets removed off of the hose, you're exposing that reinforcement. And that's bad because now you're allowing moisture and things to attack that reinforcement and it can compromise the pressure performance of that and cause potential leaks or failures where you have maybe that reinforcement being compromised in that area. So obviously, like we talked about with some of the routing exercises, just using clamps, trying to maybe bundle things together, using nylon sleeve guard or other types of guards out there, spring guards. There's various accessory methods you can use to maybe help protect, or using a higher abrasion resistant cover. A lot of hose manufacturers will have like a standard, mid, and extreme abrasion resistant cover. So those are things you can do to try to address the abrasion. Hose twist, and I won't spend a whole lot of time on this, but hose twist, and you can see it because every hose will have what we call a ley line or a label across the hose. And if you see it spiraling like that, that's bad because typically some manufacturing processes do have, like, there is a spiral ley line, especially more on the industrial hose side. But in general, if it's supposed to be a straight line and you see that it's spiraled because there is hose twist, that's really bad for a hose. I know at one point we were saying just as little as 7% twist that you get can significantly reduce, almost by 90% reduce the service life of the hose. So twisting is really bad. The hose isn't designed to be twisted. Picture on the right shows just twisting happening from motion where that back right piece is going up and down. And so a way to avoid that is just looping up vertically up and over so you can eliminate that hose twist. Sometimes when you're tightening down these assemblies and not using the backup hex, and you're torquing that nut down of the coupling, you might get a little twist from that too. So you always want to try to use the backup nut when you're installing the assembly. So here's a picture of hose twist. You can see you got a nice little twist there. It's a short length. A lot of times when you see this, you'll see two 90-degree fittings used on each end. And that's where you have hose orientation or clocking. So anytime you have two bent elbows, that has to be at the right orientation as depicted below the image here. Okay, if you don't orientate that right and you try to put it on, especially if it's a shorter assembly, it's going to be susceptible to twist because you can't move it. It's hard to move, right? You don't have much play or wiggle room. So again, you want to avoid this at all costs. It's usually a best practice as well not to have two bent elbows on the assembly for this very reason. So that's something we try to avoid, not recommend. All right, coupling installation tips. We recommend, again, following the torque specs. Again, when you have a fitting, make sure that the seat's not damaged, the O-ring's not damaged, the placement's right with the O-ring. Otherwise, you don't want that O-ring to roll or get in the way or become misaligned where it now creates a potential leak point there. So here are some examples of when you don't use the right torque specs. So this is probably good because Andy was trying to show this for that JIC2 flare. But here's an image. Again, it looks like that's a 37-degree JIC coupling end. You can see the seat is cracked. Somebody torqued down on this nut too far past that recommended torque spec and crack the nut. So obviously that's going to leak. And then again, the picture on the right, cracked nut, same thing. Somebody torqued down too much on it and cracked the nut, going to cause a leak. All right. Lastly, this is one of my favorite pictures. This is like low-hanging fruit when you walk up and see a piece of machine like this. You have lots of adapters. You have adapters stacked on adapters. Looks like there's a check valve there. And so, over time, people just hodgepodge things together, and that just becomes what it is. But anytime you add these adapters stacked on adapters, you're adding an additional leak point to the system that you don't necessarily need in there. And you can resolve through cleaning up the adapter usage, maybe using a manifold that you can plug into with all of these hose connections versus all these T's and 90-degree fittings. Because the other thing, it adds cost, yes, but it also creates a flow restriction. So now you're just adding to your overall pressure drop in the system. So you want to try to avoid that as best as possible. All right. I'll open it up if there's any more questions. Good questions along the way. Hopefully I answered those to your satisfaction while we went through.
Yeah, Chad, I'm looking at, I don't see any questions right now. I do see Paul Michael put a comment here that referring back to the clamping, is that Table 7 of the leak prevention paper provides guidelines for tube clamp spacing. Figure 12 provides a graphic illustration of proper tube clamp locations.
Awesome.
Chad,
Thanks, Paul.
I have a question, kind of a basic question, but something I was just thinking about. What would happen if somebody used a hydraulic tube in a pneumatic application? A pneumatic application. Would you get bubbles on the, like you saw in the picture?
Not necessarily, no. I would, out of caution, just maybe recommend perforation. When I think of pneumatic, I think more of some of the industrial product offering industrial hose products that we offer, where we actually have just the covers already pricked from us as the manufacturer. That would be more of an ideal solution. But the other thing too is, and not to get in the weeds, but the hose is designed really to be a hydraulic hose with hydraulic fluid in there, right? So that material we use on the inside of that hose isn't necessarily designed to work with air. We don't test it, right? So what could happen is if the air gets hot enough too, you could age the inside of that tube, right? And again, not to get in the weeds, but like a nitrile material versus like an EPDM. A nitrile is going to have a lower heat performance than an EPDM polymer. And you got to watch your temperature, I guess. So like, it's not just will the air permeate through the hose, but it's also what is the air going to do to that material on the inside? Is it going to kind of cook and age the inside quicker than what it would when there's hydraulic fluid going through there?
Mm-hmm. Did you say that in the pneumatic hoses the cover is pricked ahead of time?
Well, just to clarify, we have some like air multi-purpose hose, right? That we sell on the industrial side of the business or industrial hose market. And that, we have a pin pricker machine as the hose is produced. We have a pin pricker machine that actually perforates the cover so that when a customer buys it, they don't have to do that.
You do that with propane hoses too, don't you?
Yep. Our LP hose. We do that with a variety of different hoses where it's truly designed to have some sort of gas going through there.
Chad, we have a question in here. Someone is asking, what was the SAE standard for recommending torquing? 2 slides back. It might be more than 2 slides back now, but recommended torquing standard.
2593. Let me go back here. Or yeah. Also I'd have to double check on the connector standards. I rely a lot on my coupling development engineer to shoot off. He knows the SAE specs pretty well, but I believe some of the actual ORS and JIC might even have torque specs within them. I'm not 100% sure, but
Okay, I think that takes care of questions.
all right.
Thank you, Chad.
Awesome. Well, appreciate the time, and yeah, if there's more questions that come up, I'll be here. And Paul, you gonna kick it off to Trevor?
Yes, I'm passing it on to Trevor now. So
All right.
thank you very much. Well done. Excellent topic coverage and insights. Appreciate it. So it's my pleasure to introduce Trevor Combs, Global Technical Manager for the off-highway market segment at Trelleborg Sealing Solutions. He's got a strong background in mechanical engineering, spent 6 years as an application engineer at Micropump before joining Trelleborg way back in 2011. He's had multiple engineering leadership roles at Trelleborg. He holds a master's degree in engineering technology and management from Portland State University and a Bachelor of Science in Engineering from George Fox University. Today, he's going to share his expertise on best practices for leak prevention. And I just want to say that it's really been a pleasure working with you on the task force, Trevor, and your team.
Great. Yeah. Thanks, Paul. It's been a pleasure working with you as well. Thanks for the introduction, and good morning, everyone. So I'm going to spend a little bit of time talking about another key aspect of preventing leaks, which is sealing a hydraulic cylinder, kind of the workhorse of the fluid power system. So today we're going to cover a lot of the content in the white paper, but as well as some additional details. So we're going to focus today on dynamic sealing and kind of the 3 elements and how they interact together. So the 3 elements being the counter surface that the seal is running against, the fluid that the seal is sealing, and then the seals themselves. And then we'll talk about sealing systems and how the different components interact with each other, and then end with some seal failure modes and kind of what to look out for. So that's the agenda for today. So the paper talks about different major components and sealing those major components within a hydraulic system. It talks briefly about rotary seals, but it's really focusing on the cylinder seals themselves, and specifically the rod seals and scrapers, and because that's where a lot of the external leakage is going to come from. It doesn't talk much about the piston seals. It's not a focus since piston seals won't provide external leakage. Now, that's not to say that it's not important. Piston seals can have internal leakage, and that can cause drift or unintentional movement of the cylinder. So it is important to spec the right piston seal into the cylinder, but we're going to focus on the rod seals today. The paper does touch a little bit on static seals within the cylinders because they can be a source of external leakage. So wanted to show one of the figures from the white paper, which shows a few different static seals. So a lot of O-rings are used as static seals, but you can see that there's other options there, and some of these solutions can really be problem solvers for a static seal leakage, especially on a hydraulic cylinder. So I know Andy mentioned the dual seal, for example, which is typically a polyurethane material with 2 sealing edges that can replace an O-ring and a backup ring. And so we've seen a lot of success in eliminating leakage with an alternative static seal like the dual seal. But today we're going to focus on the dynamic seals. And so we're going to talk about the rod seals, the rod wiper, and there's the rod wear ring, which we're not going to talk too much about today, focus on the seals. So when you talk about dynamic sealing, there's a lot of factors that go into influencing dynamic sealing and specifically reciprocating sealing. So there's this German organization of industrial and research people that called the VDMA, and they did a paper a while back talking about all the different factors that influence sealing. And so you can see there's a lot of them there. It's a very complicated system. But we're not going to talk about all of these. We're just going to focus in on three kind of primary interacting elements when it comes to preventing leakage in a hydraulic cylinder and reciprocating seals. So we're going to look at the counter surface, we're going to look at fluids, and we're going to look at the seals. And these are kind of the big three. And then hopefully we're going to bring it all together and talk about how they interact with each other and how that's going to help us prevent leakage in a system. So when we talk about counter surfaces, we often think of just the surface finish, but it really goes beyond that. There's three key factors when it comes to the counter surface itself. So we're looking at the base material or the substrate, what that material is, what the hardness of it is, corrosion resistance, etc. But we're also looking at the coatings. Coating is an important part of that system, that counter surface. And then, of course, we're also looking at the finishing, and that has to do a lot with the process, but ultimately the resulting surface finish. So we'll talk about surface finish a bit. So when you look at coatings, there's a lot of different reasons to use a coating, a lot of different reasons of which coating you would want to look at. And so this is showing just some of the different reasons for using a coating. I'm not going to go through all of these, but just to give you an idea that there's a lot of different reasons why you'd want to use a coating, and it would depend on what you're valuing in your system to determine which coating you'd want to use. But you can see there at the bottom right, sealing is an important aspect for which coating you'd select. And so we want to keep that in mind when we're selecting coatings, the sealing and the impact on the sealing system. When you look at all the different types of coatings, then there's all different types of coatings, and you're trying to match up which coating do I want to use that meets my requirements in terms of the reasons for using a coating. So I'm not an expert on all the different types of coatings, but you can see there's a lot of different ones there. I'm kind of going to narrow in and just talk briefly about the hard chrome plating, which is, I think, the most common plating for hydraulic cylinders. It's based on hexavalent chromium, which is a substance of very high concern based on the REACH regulation, but people still continue to use it because it's so incredibly effective for corrosion resistance, for the hardness that it provides for the seals that they need, and the price point, so the cost effectiveness of that coating. But when you look at the substrate and the coating, it's a combination of how they go together. So if the coating is supported by too soft of a substrate, then it can crack, it can get deformed, or it can even be carved into. The coating can get kind of carved out under high pressure load. And so what we want to do is have a substrate that's hard enough that it can support that coating, and then a coating that's thick enough that it can support the seal. And so it's a combination of those two working together. So often you'll need to harden, maybe do an induction hardening process on the substrate to make sure that it has the necessary hardness to support the coating. And that coating, if it has the right thickness, it will ensure a good dynamic running surface for the seal that doesn't get damaged over time. So the coating is typically microns thick, so it's not to scale this picture, but just representative of wanting to ensure that you have the right coating and substrate for your system. And then the last kind of element of the counter surfaces is the surface finish itself. So the functional reliability and service life of a sealing system is really dependent on the surface finish of the mating surface that's going to be sealed. So it's important that meets the requirements of the seal so that you prevent leakage. Now, when we talk about surface finish, it's quite an extensive subject. There's a lot that goes into it, but there's three main surface finish elements, and that's lay, which is kind of the direction of the dominant surface pattern, like parallel grooves on the counter surface, and then waviness, which is typically made from like undulations from machine vibrations or deflections. Kind of the larger surface finish. And then roughness. So the roughness is the really tiny, sharp irregularities from tool marks from the machine process itself. And so those are typically the characteristics that we're looking at when we talk about surface finish. We're usually talking about the roughness and how it can affect the friction and the wear and the sealing performance in the system. So we're just going to talk a little bit about surface roughness. A lot of people are familiar with RA. It's probably the most common parameter used to kind of define the surface roughness of a surface. And it's pretty simple. It's the average variation from a mean line, either peaks or valleys. It's the average of those variations from the mean line. And so what you can see here is that you can have the same RA, but very different profiles, especially as it relates to the seals. So a seal is going to be affected dramatically from the different profiles there on the right, even though they all have the same RA. So what that says to me is that RA isn't alone enough to define the necessary surface finish for a rod. And so what we like to do is recommend a few other parameters. So when you're looking at the surface roughness, you want to look at a few other parameters. So the R max is one. The R max is the distance from the highest peak to the deepest valley on a surface finish. So it kind of gives you a worst case scenario, kind of what are you up against on the worst case scenario? If there's some major defect or something on the surface, it will tell you that. The RZ is an average of 5 Rmax values from 5 sampling lengths. So you kind of look at 5 sampling lengths, take the worst case scenario from the 5, and then average them out. And that kind of gives you a better view of the extreme irregularities on the surface. Not just the worst case scenario, but kind of a little bit better picture. And then RA, we already talked about, is the roughness average. That is an important part of the roughness profile. And it kind of gives you more of a good quick indication of the overall smoothness of the surface. And then we have recommendations for each parameter based on the material, the seal material that you're using. So you can see with a PTFE material, you're going to want a little bit smoother surface than like a polyurethane or rubber because it's more sensitive to that. And then another important parameter is the relative material ratio. And the relative material ratio is basically a percentage of the material at a specific depth on the surface. So you're looking to kind of do a cross-section of the surface at a level that the seal is most likely going to ride on for the most of its life. So it's going to break down some of those peaks, and then it's going to ride on a surface that's just a little bit below what the top of the surface is before it's been broken in. And so that's what the RMR is trying to provide for you, is an understanding of how much support is the seal going to have, as well as how much lubrication retention is the seal going to have. So you can see in the picture there on the right, you have a closed profile form, which is preferred and recommended. We usually say 50 to 70% RMR is ideal. And so that gives you good support for the seal. It's not riding along peaks, but then you still have valleys to hold lubrication and lubricate the seal effectively. The picture on the very bottom right is an open form, we would say, and that has an RMR of 15%, as you can see, which is not ideal for the seal and is going to wear the seal much quicker than a closed profile form. Okay, so that's talking about counter surfaces. The next element that we wanted to touch on is the hydraulic fluid. So hydraulic fluid is a crucial element in preventing leakage as well. So that's obviously the component that you want to keep in the system, but at the same time, it serves a lot of different functions. Heat transfer, contamination control. Of course, it's its primary purpose is to transmit energy through the system, transmit that work. And then it can lubricate the system, but it also helps with sealing. It assists in sealing by filling the gaps. That's why it's harder to seal a gas or a thinner fluid. And then it also lubricates the seals and provides pressure for the seals. So a lot of the seals that you'd use utilize the pressure to energize the seals themselves and give them the function that they need. So the hydraulic fluid is an important part of preventing leakage. So a few things to look at when you're looking at hydraulic fluids in a hydraulic cylinder is fluid compatibility. So you want to make sure that the seal materials in the hydraulic fluids are compatible. If they're not compatible, you can see swelling, you can see shrinkage. And with a lot of the fluids now, there's a lot of ingredients, a lot of additives, a lot of different things that you're not always sure how they're going to interact with the seal materials. So it's important to have some testing or some baseline understanding of how that material is going to perform with the fluid that you're using. And then a last point on this slide, the temperature directly influences compatibility. So a material that might be compatible at one temperature, as that temperature increases, may not be compatible at a higher temperature. So it's important to look out for that as well. And if a seal swells or if it shrinks, it's not going to fit in the groove correctly. It's not going to perform as it was designed. And so that's going to lead to leakage. Another important aspect of the hydraulic fluid is the viscosity, because the viscosity directly influences the hydraulic fluid film. And we're going to talk a bit about the hydraulic fluid film that you need under the seals to lubricate the seals to ensure performance. And so the viscosity is key to that functionality. And temperature also directly influences viscosity. And so the viscosity index, I'm sure most of you are familiar with, is a measurement of how that viscosity changes in a specific fluid with the temperature change. And so you're going to want to make sure you're specifying a fluid that's going to have the right viscosity to meet the needs of your application, depending on the temperature range of your application. So that's very critical as well. And then lastly, for fluids, contamination is really key. I think a lot of failures are due to oil contamination. And as you can see on this graph, contamination can come from a lot of different sources. I think we typically think of contamination as just particles, ingress into the system, particles getting into the system. But it's a bit more than that. It can start with a dirty oil, or maybe there's water or air that got into the system, whether it's dissolved or undissolved air that can affect the sealing, the seals, and the leakage prevention. It also is important to note here that the contamination can come from internal sources as well. So we see that quite a bit where there's component wear in the system, and that's creating particles that then get embedded into the seals and can cause additional damage, either to the hardware or to the seals, to the rod, creating scratches, and those can eventually become leak paths. So contamination is an important factor to keep in mind. And I think it's important to understand where that contamination comes from, where that source is, and so you can eliminate that source. All right, and then the last kind of element that we're talking about here, we talk about counter surfaces, we talk about hydraulic fluid, and then of course the seals themselves is very important. And so two of the main parameters affecting sealing is the material of the seal and the geometry of the seal. And so that's kind of what this figure is highlighting. This figure is in the white paper. And so it's talking about the rod seal specifically. And so I have that graphic on the left to kind of zoom in and show you which seal we're talking about. So that seal can either have elastomer contact, a polyurethane contact, or PTFE contact. And so those are the three primary columns shown in the graph. And it's a very representative graph. It's a generalized graph, but it gives you a good indication of if you have an elastomer contact versus like a PTFE contact, you're going to have higher friction, higher wear, but better leakage control with the elastomer contact. And then PTFE, you can typically handle higher speeds. You're going to have lower friction, but there's less leakage control. And so it's important to understand what the trade-offs are, and when you're selecting or designing seals, to make sure you're optimizing that system and balancing the trade-offs there. And I think that's why polyurethane contact is such an often selected material, such a preferred material, is because it does give you that balance of the good, leakage control, but also good wear resistance. Good friction, can handle higher speeds, not too high of friction. So that kind of gives you an idea of the different types of geometries and the different types of contact when it comes to seal materials. Okay, so now we're going to try and pull all this together. So we're looking at the counter surface, the fluid, and the seals. And so here's a diagram of how they interact with each other. So this is a diagram of a static seal. So the fluid pressure is going to exert a force on the seal and the mating surface. But at the same time, the seal is exerting contact stress on the fluid, producing a shear stress on that fluid that's going to cut that fluid film down to zero. And that's kind of the point in the design intent of the seal is to cut that fluid film down to zero so you don't have any leakage. And that's kind of the goal. So it gets a little bit trickier and more complicated when you talk about dynamic seals, though. And that is that you actually want a fluid film under the seal, the entire length of the seal. You don't want to cut that fluid film to zero because then your friction and your wear is going to go up significantly. And so in the top here, we have it's showing the fluid film out on the outstroke. And if the fluid film thickness on the outstroke is greater than on the instroke, we're going to see leakage. If the fluid film thickness on the outstroke is less than on the instroke, then we're going to have high friction and wear. And so it really is an optimization, trying to balance the different the different parameters, the different requirements for a system, leakage, friction, and wear. And friction and wear can lead to higher, shorter life. Friction and wear can lead to shorter life, which is going to lead to leakage as well. So we're wanting to balance these elements so that we don't see like weepage from a fully lubricated system that every stroke is going to leave a little bit of fluid outside the system. But we also want to reduce friction and wear so that we don't have a seal that wears out prematurely and then has significant leakage at its end of life. I think the other thing I was going to mention on this slide is that the fluid film can help with reducing stick slip, but you want to make sure that you're getting that fluid back into the system and keeping the fluid film under the seals, and back pumping is an important way to do that. And we'll talk a little bit more about back pumping. And so that leads to looking at a sealing system overall. So often we tend to think about the different elements. You have the rod seals, you have the piston seals, you have the rod wipers, but really I think it's important, and what I wanted to convey in this webinar is that it's important to look at the full hydraulic system. You're looking at the counter surface and the fluid, you're looking at how the different seals work together, and that system can really be optimized depending on what the careabouts are, what the needs are in the system. Obviously, with the ultimate goal of trying to increase uptime and prevent leakage. So if you kind of dive into what that means, we've seen a few cross sections of sealing systems already. So this is one with a tandem seal arrangement. And this is just an example of how the different seals might interact with each other. So you have a primary seal here, which is going to have low friction, but it's also there to kind of, or like a buffer seal to catch most of the pressure. It's going to let some of the fluid pass to the secondary seal, but it's going to buffer that pressure. And then the secondary seal there is to really cut that fluid film pretty much to zero. It might let a little bit by for the scraper to ensure that it has fluid film underneath it to reduce that friction and wear. But these elements are working together, and the guide rings there, or wear rings, are there to support the seals, and that's critical. As we'll see later, if you don't have the right support, that can lead to metal-to-metal contact and particles and contamination in the system. And the scraper is another important element because it needs to keep the dirt out, but it needs to let the fluid film back into the system. And so there's a lot of design work and that goes into the scraper as well. So you can see from this picture just that there's a lot of different elements going into the sealing system, a lot of different interactions. And so we want to understand those and how they work and optimize that for your system. So what I'm going to do next is just talk about 3 different examples of design features in the sealing system that can be really helpful to preventing leakage. So the first one on the buffer seal is it can be really helpful to have a buffer seal design that can relieve back pressure. So this is the primary seal or buffer seal. Those terms are used interchangeably. But having a relief mechanism that can activate when the pressure is trapped between the seals. So sometimes that pressure in between the seals will actually build up over time. With each cycle, with each stroke, there's going to be potentially pressure building up between those seals. And so if that pressure increases to the point that it's above the system pressure, you need a way for that pressure to relieve itself back into the system. And so that's what this seal is showing. It can, when the pressure gets to a certain point where the pressure on the right is greater than the pressure on the left, that pressure will relieve back to the system. And so that's an important design that can prevent extrusion of the secondary seal. And then next, we've talked about this a little bit already, but the fluid film is important to manage. And this is just a representative picture of the fluid film principle, that you want a little bit of that fluid film to pass by the primary seal to lubricate the secondary seal. And so making sure that you're optimizing the system to allow for that fluid film to come by, past the primary seal, but then be pumped back into the system so you're not getting weepage outside of the cylinder is really key. So you can see here on the top, we have a primary seal that's not letting any lubrication past, and you see the friction results there on the right. And if you can design a system effectively that it's allowing the fluid film to support and lubricate all the seals in the system, then you can really greatly reduce your friction. But you need to make sure that it's optimized to get that fluid to stay inside the system. And so that's where the optimization comes in. The next kind of key feature that can be really helpful on a sealing system and seals specifically is the back pumping technology. So in back pumping technology, on the forward stroke, the oil lubricating film is distributed under the seal as it goes out of the system. And then on the return stroke, that oil, you want to be pumped back into the system so that you don't have that leakage that we're talking about. And that can extend the seal life by reducing the dynamic friction and the breakaway force, the stick slip, even like I said. And so this video is showing a test where we were using a back pumping seal to show how much fluid can be back pumped. Obviously, this is sped up, but you can see with the cycle, as it cycles, the rod cycles back and forth. It's actually pumping some of that fluid in the reservoir back into the pressurized portion of the system.
Hey, Trevor, we have a question.
Yeah.
And it probably relates right here, is we have seen situations where the rod is very dry upon extension and friction is very high during retraction. Would a rougher surface be better for leaving a little bit of oil to remain on the rod?
Yeah, that's a good point. So I think it might be important to look at the RMR that we talked about. I mean, there's a lot of factors that could be going into why that's happening. But the relative material ratio, if you don't have valleys that the lubrication can stay on the counter surface to lubricate the seal, then you could be seeing higher friction. It could also be something relating to the velocity ratio, and we'll talk about that a little bit later, is if you have a lot, if your velocity ratio isn't balanced in terms of it's going faster out and then slower in, or slower out and faster in, that can affect that lubrication film and how it stays under the seal. So those would be the two things that come to mind if you're getting a variation in friction between the strokes. So hopefully that helps. And so understanding the application parameters and what your stroke lengths are, what the speeds are, what the fluid is, what the temperature range is, those are all going to be important factors in determining which seals you want to use for the system. Yeah, good question. Okay, so moving on to kind of the last design element that I wanted to talk about. There's lots that we could go into, but just kind of highlighting three. So this is if you have pressure buildup between that secondary seal and the wiper. If you have pressure buildup between those two seals, you can actually push the wiper out of the groove. And we've seen that quite a bit, actually. So it's important to have the back pumping feature can help relieve that pressure buildup, but also you can have a venting feature within the scraper that can help relieve any pressure if it builds up between those two seals, so you don't get the wiper pushed out of the groove, because that will lead to extensive external leakage typically. And so what this design functionality does is, as the pressure hits the wiper and starts to build up, instead of getting to the point where it pushes the wiper out of the groove, it actually has a valve integrated into the wiper that will relieve some of that pressure. So you will get a little bit of fluid relieved out into the environment, which isn't ideal, but it's much better than having the wiper getting pushed completely out of the groove, and then you have a huge leakage problem. And so I think wipers are especially sensitive to being pushed out of the groove, because as you can see in this picture too, especially, there's a little bit larger clearance there. So less support for the wiper can, instead of extruding, it would actually potentially get pushed out of the groove, which can lead to a lot of leakage. Okay, so lastly, we're going to look at how all these elements work together within a sealing system by looking at a few examples of different sealing systems. So this is an example of kind of a more basic but very common polyurethane rod sealing system that would be used for more light to medium duty applications. It has a back pumping U-cup in there and a double acting scraper. You definitely need a wear ring in there for support, and this would be a typical sealing system for those types of applications. Here's another example, a little bit higher pressure, maybe a more medium to high heavy duty application where you have a primary seal that's taking a lot of that pressure. You can see all these seals are pressure energized with that U-cup sort of shape to it. But so this is a common example for a system that can handle a little bit higher pressure, but still all polyurethane seals. Now, if you want to go into a little more of a premium solution, or for unique applications, for more, if it's medium to heavy duty, but also high speeds, for example, you might use a PTFE solution. These can be really effective, low friction, low wear type seals that can be used for really high speeds. So that can be a good option. In this system, it's combined with a polyurethane secondary seal to still provide good leakage control, and those can really balance each other quite well. So we've seen a lot of success with this type of system as well. And then lastly, more of a real world example for bucket arm and boom cylinders. You can see the pressures there. You can see the speeds, and this is where I mentioned the speed out sometimes is often greater than the speed in. And so you have to be aware of that and how that's going to affect the fluid film. Because if the speed out is significantly greater than the speed in, then there's more likely to be leakage. But if the speed out is much greater than the speed in, then that's going to lead you to lower friction, because that lubricating film isn't going to be under the seal as much. So yeah, based on the pressures, the speeds, and the lifetime requirements, this system required a tandem sealing design that had both a primary and secondary seal with a double acting scraper. All right, and so for the last few minutes here, I was going to touch on some of the failure modes that comes with seals. And I'm not going to talk about all of these, but wanted to show kind of a pretty extensive list. Well, I'm going to focus on these four and just have a few slides showing different types of failure modes, and then we can talk a little bit about what to do regarding them. So the first one is extrusion. So I have some pictures of PTFE seals and some acceptable extrusion on the left and not acceptable extrusion on the right. So with PTFE seals and really high pressures, we can expect some extrusion or creep, we call it, as the material moves over time with pressure, heat, and wear. But if there's too much extrusion, that can cause the seal to start leaking and no longer perform as designed. For rubber and polyurethane, they're going to look a little bit different. If you're operating the seals outside of their application limits, or if there's excessive clearances, too much pressure, too high temperature, they can start to extrude. So rubber seals, you'll see little chunks kind of torn off. It's where we call it nibbling, where the pressure is forcing that rubber into the gap, and then it's getting kind of torn off. Polyurethane seals will tend to more like shear, like come off in slivers or be pinched or deformed. Those are all signs of extrusion. And so you want to look at addressing either the design, the pressure, the clearances, misalignment potentially could be another cause. And then for contamination, like I said before, it's a it's a very common cause of failure and critical to address. So you can have debris ingression that can be caused from external sources or internal sources. And so you can see a picture on the left is a wear ring that got scratched by some hard particle, and that can cause damage to the hardware, to the seals, those hard particles getting in. The pictures, kind of both of the pictures on the top more are pictures of O-rings or other elastomers that have metal particles embedded. And once they get embedded, then they can start scratching the surface as well. So that can cause leakage. And then we have a wiper in the bottom there, bottom middle, that got painted, and that paint can be a source of contamination as well and cause the seal to not function as intended. And then in the bottom right, we have some shavings from a machining process where kind of an extreme example, but sometimes there's shavings or other contamination that comes from components that are installed or assembled, and that's where cleaning out the hoses, like Andy talked about, and making sure that you have clean those up before you install them so you don't get contamination into the system. And also filtration is key for that as well. And then I mentioned misalignment, but if you have too much misalignment, you can have metal-to-metal contact, and that's obviously going to create metallic particles in the system that can cause damage to the seals. But misalignment can also cause uneven wear on the seals, where on one side you might be having heavy wear, on the other side you may not even be having contact with the seal. And so it's important to make sure that seal is aligned, and that's where having good wear rings, good bearings in the system can help ensure alignment, and so you don't have metal-to-metal contact or uneven wear on the seals. Here's an example of a misalignment on a PTFE seal, where in some of these pictures you can see the sealing edge, and in others it's worn away. So you'll have heavy wear on one side and possibly no contact on the other. And then last, but definitely not least, we see a lot of improper installation. And so kind of lumped in here is both the installation issues, like you can see kind of in the middle right in that hole there in the piston in the rod kind of section. You can see a rod seal. I was trying to point to it here that hasn't been fully installed. It's kind of sticking out of the groove. So when you insert that piston rod, it's going to shear that seal, and it's not gonna seal effectively. You can see examples of seals getting scratched here on the left. If the surface finish or the chamfers or the radiuses aren't nice and smooth, you can cause damage to seals during assembly or during installation. And then installing the seal backwards. So it's always important to make sure that the seal is installed in the right direction. We had a little FEA here of a step seal being installed backwards. So it's important to be aware of that. You'd be surprised how many times the seals can be installed backwards. But it's not going to work as intended if it's not installed in the right direction, and that can lead to deformation, or just it's not going to have the features that were designed into it, whether it's back pumping or maintaining that lubrication film. So it's not going to work as intended, and then there'll be leakage. So in conclusion, the goal is to optimize the sealing system to maximize performance and reliability. And as we saw, these systems can get quite complicated with all the different elements that are working together and affecting each other. So we would really encourage everyone to reach out to sealing experts for helping you design your sealing systems. Bring us in early so we can help ensure that we get the right seals in there, have the right space to kind of meet your needs, meet the application needs, and really get the best solution for the application. So appreciate everyone's time and attention, and I'll pause here to see if there's any questions.
Yeah, Trevor, we have a series of questions, and I'll ask this one that just came in first because it related to that last concept you were talking about is how can you tell which one is backward? I think it was on that last where you right there.
Mm, yeah. Okay, good question. Yeah. So let me play the video again. So you gotta go back one more. Okay, so yeah, I mean that's a good question because if maybe you're not familiar with seal design, what you want is you can see the X there where the contact, like the first contact is made. Let me see if I can point to it. Can you see the hand here?
Yes.
Yeah, so one of the main kind of designs of a seal is that you want to have a sharp edge where the fluid is coming in contact, and that's going to prevent the fluid from passing back past that sharp edge. And then you want a kind of a shallow edge, I'll say, to let the fluid be back pump into the system. And so you kind of don't see that. You see that on this design on the left, but you don't see it on the design on the right, where it's not going to have a sharp edge that's going to prevent the high pressure fluid from being kind of cut off or blocked by the seal. Um, and on the other side, you have the higher contact pressure actually on the right side. And so what it's going to do is allow fluid past the seal, but then when it tries to, it won't allow fluid back into the system. And so it's the opposite functionality of what you're trying to do.
If you stay on that for a moment, Trevor,
Yeah.
this might be relate to this next question as well. It's about back pumping. Is there a solution for a case in which speed out is more than speed in application to avoid leakage or avoid wiper rollout?
Yeah, so that's where back pumping would come be really effective. So if the speed out is faster, you're going to have more fluid film going out than coming in, and so you want to be able to back pump that fluid as it comes in back into the system. So it's a combination of having a back pumping seal, but also having a scraper that doesn't have too sharp of an edge. I kind of alluded to it, but you want a scraper that has the right kind of optimized sealing edge so that it still keeps the debris out, but it's not so sharp that it cuts that fluid film, and so it can allow some of that fluid back into the system. So having a kind of a system that has the right scraper combined with a back pumping seal, I think would be key for a system like that.
Okay, we've got a couple more questions here. Someone's asking whether you can share the link to there was a VDMA paper referenced earlier, I think.
Yeah, I can find that. I don't have that handy, but I can find
Okay.
that. Yeah.
We'll be sending out an email with the recording, a link to the recording and to the task force paper. And then if you can find that, then we can send that all out at once.
Yeah, definitely.
Okay. Someone asked a little bit, and this was earlier, whether the commentary is for linear only, or can you comment on rotary seals?
Yeah, for the scope of the webinar, we decided to focus on linear seals. Rotary seals are often obviously very important as well, using hydraulics, pumps, and motors primarily. So yeah, there's a little section in the white paper on rotary seals, so I definitely encourage you to check that out. But we have, I could definitely help if you want to, if you have any rotary sealing needs, reach out to me directly. I'd be happy to help. We have extensive uh, catalog of rotary seals that we could use depending on what the application is. So typically those would be high performance, high pressure rotary shaft seals. We also have a line of PTFE contact seals especially for like swivels. Those are real common. Um, yeah, so a lot of different options there. But it was outside the scope of this webinar. There's a little section in the white paper on rotary seals, but
Yeah, it
that's a
looks
whole
like
that's a whole nother topic. There's a lot of different dynamics and design features that go into rotary seals.
right. It also looks like the person was asking a little bit about surface finish in relation to rotary seals. Right.
Yeah, there
Yeah.
will be different surface finish recommendations. Rotary seal is different because it's, the shaft is spinning and the seal is sitting on the same location of the shaft the whole time versus rod seals, the shaft is moving back and forth. And so it's covering a lot more surface area of the shaft. So there are different recommendations for surface finish between reciprocating seals and rotary seals.
Mhm. This is a question that might be, I think, are there any recommendations for finding suppliers who have the capability of meeting sealing surface roughness recommended? And I would imagine that gets into a little bit of other than going on
Yeah.
eBay, finding a trusted supplier, right?
Yeah. No, we get that question a lot, and there are some good suppliers out there. I probably the best way to handle that is maybe have that person reach out to me directly. I can put my contact info in the chat, my email and phone number, and yeah, love to have a conversation more about that. But it is challenging for sure to get that right surface roughness. So there's some tips that we can provide in terms of how the finishing process, like roller burnishing is a good process to use. But depends a lot on the coating and the material that you're using as well. So yeah, I probably just leave it at that. But
Yeah, I
that's a
would say,
great question.
so Trevor, I would note that there's quite a few sealing companies, companies that make seals that are members of NFPA, and our online member directory would be one place to look. But also, I'd imagine that you have a lot of companies, and they do as well, that develop a relationship over time, so that they work with you and understand what you have to offer. Correct?
Yeah.
Okay. That I think is all the questions we have on here.
All right, great.
Nice job, Trevor. Well done.
Thank you.
I want to thank Andy and Chad for their contributions to today's webinar. It was excellent. And I want to thank all of you for attending the webinar. If you want to get your CEU or PDH, just send me an email and we'll give you a certificate for that. Look for an email from Eric. He will send you a link next week sometime where you're going to see how to get to the white paper as well as a copy of the recording of what we covered today. So in the meantime, I'd just like to thank you all again and wish you a very happy, healthy, and prosperous, leak-free new year. Thank you very much.
Thanks, everyone.
Thanks. Have a good holiday. Bye.